Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of 20th century physics, few theoretical edifices stand with the same combination of elegance, explanatory power, and profound influence as the microscopic theory of superconductivity. For nearly half a century following Heike Kamerlingh on this startling 1911 discovery of a material exhibiting a complete absence of electrical resistance at cryogenic temperatures, the phenomenon remained a tantalizing and deeply frustrating enigma. It represented a macroscopic quantum state of matter, yet it defied every attempt at a fundamental explanation. The 1958 publication in Physical Review by John Bardeen, Leon Cooper, and John Robert Schrieffer, titled simply Theory of Superconductivity, represented the definitive intellectual conquest of this frontier. This work did more than solve a long-standing problem. It introduced a new paradigm for understanding collective quantum phenomena, providing a conceptual toolkit whose resonance would extend far beyond the cold confines of condensed matter physics into the exotic domains of nuclear structure and the standard model of particle physics. The Bardeen-Cooper-Schrieffer theory, or BCS theory, stands as a monument to the power of many-body quantum mechanics, a testament to how a subtle, counterintuitive interaction at the microscopic level can give rise to a spectacular and robust macroscopic. The landscape of theoretical physics prior to 1957 was littered with the wreckage of failed attempts to explain superconductivity. The prevailing model of electrical conduction, the block theory of electrons in a periodic potential, which so successfully described normal metals, offered no path toward understanding a state of perfect conductivity. Early quantum mechanics seemed to make the problem harder, as it provided numerous mechanisms for electrons to scatter, making the resistanceless state appear all the more miraculous. The first significant theoretical progress came from phenomenology. In 1933, Walter Maesler and Robert Ochsenfeld discovered that superconductors do more than conduct perfectly, they actively expel magnetic fields, a phenomenon that bears their names. This discovery indicated that superconductivity was a true thermodynamic equilibrium state, a deeper reality than perfect conductivity alone. This led Fritz and Heinz London to formulate their celebrated phenomenological equations, which described the electrodynamics of the superconducting state with remarkable accuracy. The London equations posited a supercurrent carried by a rigid fluid of superconducting electrons, but they gave no clue as to the microscopic identity of this fluid or the mechanism that held it together. The puzzle deepened for 2 decades until a crucial experimental clue emerged in 1950. Work by Manuel Maxwell and, independently, by a group at Rutgers University, revealed the isotope effect. The critical temperature at which a material became superconducting varied with the inverse square root of the mass of its constituent ions. This was a Rosetta Stone. It provided the first concrete evidence linking the purely electrolytic phenomenon of superconductivity to the mechanical vibrations of the crystal lattice, the phonons. The path forward, it seemed, must involve a coupling between electrons and these lattice vibrations. The intellectual architecture of the BCS theory rests upon 2 foundational pillars, erected in sequence. The first was the conceptualization of the electron-phonon interaction as a source of attraction. An electron moving through a metallic crystal lattice, a sea of mobile negative charges within a framework of positive ions, repels other electrons via the powerful Coulomb force. However, its passage also perturbs the lattice itself. The negatively charged electron attracts the nearby positive ions, pulling them slightly from their equilibrium positions. This creates a small, localized region of excess positive charge, a deformation that propagates through the lattice as a quantum of vibrational energy, a phonon. This region of positive charge can then attract a second electron. The net effect is a subtle, time-delayed attractive interaction between the 2 electrons, mediated by the pliability of the crystal lattice. For this attraction to overcome the ever-present Coulomb repulsion, it must occur between electrons with specific properties, typically those near the surface of the Fermi sea of occupied electron states. This interaction, first proposed in a rudimentary form by Herbert Frey, became the central dynamic mechanism. The second, more decisive pillar was Leon Cooper's 1956 calculation. Cooper considered the problem of 2 electrons existing just above a quiescent, filled Fermi sea. He demonstrated with mathematical certainty that any arbitrarily weak attractive interaction between them would bind them into a new quantum state, a Cooper pair. This result was profoundly counterintuitive. In free space, a weak potential fails to bind particles. The presence of the Fermi sea, with its Pauli exclusion principle forbidding the pair of electrons from occupying lower energy states, changes the physics entirely. The resulting Cooper pair is a composite entity with distinct properties. The constituent electrons have opposite momenta and opposite spins, resulting in a pair with 0 total spin and 0 total momentum. This makes the Cooper pair a boson, a particle that is exempt from the Pauli exclusion principle. This was the key if electrons could form bosonic pairs. They could then all condense into a single, shared quantum state, forming the macroscopic coherent fluid that the London equations had hinted, with the concepts of a phonon-mediated attraction and the resulting Cooper pair in hand. The final challenge was to construct a full many-body theory. The task fell to John Robert Schrieffer, then a graduate student working with Bardeen. A simple picture of independent pairs was insufficient, as the average distance between electrons in a Cooper pair is quite large, meaning the pairs overlap extensively. One cannot treat them as distinct entities. Schrieffer's solution was an act of profound physical and mathematical insight, a variational ground state wave function that described the entire system of electrons. The BCS ground state wave function is a coherent superposition of states. It is constructed as a product of all possible momentum states, where for each momentum k, there is a superposition of the state being empty of a pair and the state being occupied by a Cooper pair with momenta k and negative k. This complex wave function represents a sea of electrons where every single electron is paired with another. The probability that any given pair state is occupied is described by a set of parameters that are chosen to minimize the total energy of the system. This formulation was a masterstroke, capturing the collective, correlated nature of a superconducting condensate. The most important consequence derived from this wave function was the prediction of a superconducting energy gap, typically denoted by the Greek letter delta. This gap represents the minimum energy required to break a single Cooper pair and create two independent particle-like excitations, known as quasi-particles. The BCS theory provides a specific equation for the size of this gap at zero temperature, showing it to be proportional to e to the power of the negative reciprocal of the product of the density of states at the Fermi level and the electron-phonon interaction potential. The existence of this energy gap is the ultimate source of superconductivity's remarkable properties. For a current to dissipate energy through scattering, an electron must transition to a different energy state. In the BCS ground state, there are no available energy states below the gap energy. A small perturbation, like scattering off an impurity, lacks the energy needed to break a pair. Consequently, the collective motion of the Cooper pair condensate is protected, and the supercurrent flows without dissipation. The theory's publication was met with immediate and widespread acclaim, for it succeeded in explaining, with quantitative precision, the entire suite of known superconducting phenomena. The zero resistance and the persistence of supercurrents were direct consequences of the energy gap. The Meissner effect, the expulsion of magnetic fields, was understood as a collective diamagnetic response of the condensate. Applying an external magnetic field raises the kinetic energy of the paired electrons, and the system finds it energetically favorable to generate screening currents on its surface to precisely cancel the field in its interior, preserving the low energy gapped state. The theory also provided a direct derivation of the isotope effect, because the attractive interaction is mediated by lattice vibrations, whose characteristic frequency, the Debye frequency, is inversely proportional to the square root of the ionic mass. The theory naturally predicted that the critical temperature would exhibit precisely this dependence. Furthermore, it correctly predicted the specific heat of a superconductor. In a normal metal, the specific heat is linear with temperature. The BCS theory predicted that as a superconductor cools below its critical temperature, its specific heat would exhibit an exponential decay, characteristic of a system with an energy gap, preceded by a sharp, discontinuous jump at the critical temperature itself. Experimental measurements confirmed these predictions with stunning accuracy. In one stroke, Bardeen, Cooper, and Schrieffer had transformed superconductivity from a mystifying anomaly into a beautifully intricate, yet fully understandable, consequence of the laws of quantum mechanics. The legacy of the BCS theory extends far beyond its initial domain. The conceptual framework it introduced, particularly the ideas of a spontaneously broken symmetry and a gapped ground state, proved to be of fundamental importance across physics. The BCS ground state is a state that lacks the full symmetry of the underlying laws of physics. It has a definite phase, a property the original Hamiltonian does this. This concept of spontaneous symmetry breaking was seized upon by Yuichiro Nambu, who recognized its deep parallel with problems in particle physics. Nambu applied these ideas to explain the origin of the mass of nucleons, proposing that the vacuum of quantum fluid dynamics behaves analogously to a BCS superconductor. This work laid the foundation for the understanding of chiral symmetry breaking and led to the formulation of the Goldstone theorem. The intellectual lineage continues directly to the Higgs mechanism, the cornerstone of the standard model of particle physics responsible for giving mass to elementary particles like the W and Z bosons. The Higgs field, which permeates all of space, acts like a condensate. Particles moving through it interact and acquire an effective mass, an idea that is a direct conceptual descendant of an electron quasi-particle acquiring a minimum energy, the gap energy, in a BCS superconductor. The pairing mechanism itself also found application in nuclear physics, where a similar pairing interaction between protons and neutrons helps to explain the binding energies and stability of certain atomic nuclei. The BCS theory provided a concrete, solvable model of a complex quantum system. The lessons learned from it became a universal language for describing emergent order in nature. In conclusion, the 1957 theory of superconductivity by Bardeen, Cooper, and Schrieffer remains a pinnacle of 20th century theoretical science. It solved a problem that had perplexed the world's finest minds for nearly 50 years, transforming a collection of bizarre experimental facts into a coherent and predictive theoretical structure. Its power lay in its microscopic foundation, tracing the spectacular macroscopic quantum phenomena of zero resistance and magnetic field expulsion back to a subtle, phonon-mediated attraction between electrons. The central concepts of the Cooper pair, the coherent May-body wave function, and the resulting energy gap provided a complete and quantitatively successful picture. The work's influence was immense, providing the intellectual seeds for the theory of spontaneous symmetry breaking that now underpins our understanding of the fundamental forces and particles of the universe, while the subsequent discovery of high-temperature superconductors in materials where the electron-phonon mechanism is thought to be insufficient has opened new chapters in the story of superconductivity. This development in no way diminishes the pristine intellectual achievement of the original theory. It merely delineates its domain of applicability and highlights the richness of the quantum world. The BCS theory stands as a perfect synthesis of experimental insight, mathematical ingenuity, and profound physical intuition, a lasting monument to the human capacity to unravel the intricate secrets of the quantum realm.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.